we have a long pole with a sort of a spoon on the end and a lot of heat-proof gear that we put on.
You're listening to The Cosmic Cast. Hello and welcome back to another episode of The Cosmic Cast. I'm John Penny-Fisher and I'm joined by our regular co-host of Elliot Carter, who's right over here. And this week, all the way from the University of Iceland, joining us is Dr. Simon Matthews. How's it going?
Good, thanks. Thanks for having me.
No, it's a pleasure. Absolutely. So we were just chatting a little bit before we started recording. Yeah, I think, Iceland and its latest eruption's been in the news quite a bit. It's not really something we've covered in this podcast before. So I thought it'd be great to have you on to chat a bit about why Icelandic geology is so exciting, really. So firstly, I guess a bit about you. So you're based at the University of Iceland. I guess, how long have you been there now? So I guess you're from the UK originally.
Yes, so I moved to Iceland in August of last year.
Okay. Oh, quite okay. Not too long ago then.
Really a few months before the eruption kicked off.
Good timing.
Yeah, really good timing.
What's it like living in Iceland? It must be such an awesome place to work as a geochemist and as a volcanologist.
Yeah, I really like living in Iceland. I guess the majority of the population lives in Reykjavik, which compared to most towns or cities in the UK is quite small. It's very similar size to Cambridge, I guess. So, and that's really the only main infrastructure in the country. So it can feel a bit isolated at times, but I really like living in a small city. And sometimes the weather's quite good, sometimes or often it's not so good. But there's plenty of opportunities to get out of the city and see rocks, or just to go and enjoy the countryside as well, which I really value.
Yeah.
Imagine.
Yeah, that's awesome. So obviously, Iceland is known for all its volcanoes and stuff, and so it brings us on really to the main event. I guess we've had this quite a sizable eruption quite near Reykjavik then occurring. I mean, how long has it been going on for now? It was sort of March-ish time it started, wasn't it?
Yes, I think it's just past the 3-month mark. So the eruption started in this valley called Geldingadalir, which is in this mountain range called Petrographic. And so at the start of the eruption, we were all calling it the Geldingadalir Eruption in anticipation of it being officially named. And that name worked whilst the eruption was just contained in this one valley. But then a few weeks after the eruption started, new vents opened up, and suddenly the eruption is now distributed across a much larger area for Geldingadalir. So that's the name that we've adopted now. So Geldingadalir Eruption.
Yeah. I guess Icelandic eruptions are a frequent occurrence. Is this sort of made a bit more traction in the news just because of its proximity to Reykjavik, or do you think?
Yeah, I guess it's usually an eruption every 4 years or so on average. Obviously, it varies a lot. And the last eruption was Fluorine, which is in the northern volcanic zone of Iceland. So that's the area of Iceland that extends northwards of the big glacier Vatnajökull. And you can get to the very top of the northern volcanic zone where it meets the coast, but once you start moving towards the glacier, it becomes very inaccessible and quite difficult to get to. And so though this eruption was happening over quite a long time, very few people could actually get there to see it.
I guess it's all sort of dirt roads and beefy 4x4s required, isn't it?
Yeah, exactly. Whereas this eruption, I mean, in the early days, it was a long hike to go and see it. But you could drive there in an hour from Reykjavik. But now, sometimes you can even see the eruption from downtown Reykjavik itself.
Oh, wow.
Yeah.
And as the eruption grows, the hike in to see it is getting shorter and shorter.
Yeah, I mean, some of the photos that I'm sure some of the viewers would have seen on Twitter are absolutely phenomenal, aren't they? With the city skyline and then the fire fountaining in the background. Are people quite worried that it might encroach into the city itself, or is it still a fair enough distance away? Or
so there's, at least at the moment, there's not much concern that it will impact any settlements. The photos that you see, the Reykjavik skyline in front of the eruption, I guess there's some very fancy camera technology they're using to do that, and it's that when you're standing here, it certainly looks much further away than those photos here, which is reassuring.
Yeah.
But the closest town to the eruption is Grindavik, which is a very small place. And even there, it's very unlikely that the eruption will get anywhere near the town. The thing that we're waiting for at the moment is for the lava flow to reach the main road that goes along the south of the Reykjanes Peninsula. And there's been a lot of debate about whether we should try to stop the lava and try to divert it somehow, or whether we should just let it take over the road and deal with it afterwards. And that seems to be the choice that the officials have made. Is it'd be too expensive and too uncertain to try to influence where the lava's going.
Yeah.
So that's likely to happen in the next few weeks, would be my guess.
Oh wow! So it's moving at quite a pace then, really.
Yeah, it's hit another valley now called Nautai, and that's pretty much all downhill, more or less, towards the road.
Mm-hmm.
It's just spreading out and not really getting banked up against anything.
So is this in terms of sort of, I guess, past recent eruptions, is quite a big one then, would you say?
So compared to Holothrain, the mass of lava that's coming out of the vent at any one time is, I think, maybe an order of magnitude smaller.
Oh, okay.
Really?
So by Icelandic standards, it's actually quite a small eruption, but it's, I guess, because as long as these eruptions go on for a long time, you can just build up the volume quite substantially.
Yeah, it's been amazing just watching how that volcano that first appeared changed just over a matter of days and then weeks, and now it's sort of unrecognizable.
Yeah, I mean, where we were standing, the first time I visited, I think it's now under tens of meters of lava.
Wow.
Which is incredible.
So I guess with this brand new volcano, it's been an amazing opportunity to go and sample some of the youngest rocks on Earth. What are some of the things people are doing on them?
So the group that I work in, which is the geochemistry and the petrology group, and we've been trying to get samples. And at the start of the eruption, we were doing it every few days. Then we changed to trying to get samples every week, and now we're doing it maybe every week or 2 weeks, depending on when we can get out there. And the reason we're doing that is so that we can see any changes in the lava that's coming out. As once I guess if you don't go and get the samples right then, they could be buried and you'll never be able to sample them again, at least not without some very expensive drilling. And so we're trying to build up this sample set.
So this is this sampling that's I mean, are you waiting for the lava to solidify it somewhat, or is this sampling actual molten material still?
So we do both. Where we can and where it's safe to do so, we'll go and actually get some of the molten magma and quench it ourselves in a bucket of water. So we have a long pole with a sort of a spoon on the end and a lot of heat-proof gear that we put on. And you can go and scoop up some of this gloopy magma, and that really does feel like that. It's like treacle or something. Putting a spoon through treacle.
That's quite amazing, actually. There can't be many people who know what dipping a spoon into lava feels like. I don't know.
That is cool. Yeah.
And so, but often we can't do that. We can only really do that where the lava is flowing out on relatively flat ground, and where you're getting more hoi-hoi-like flows. So you've got sort of gentle flows where you might get a skin on top, but you can break through the skin and it's molten underneath. Whereas other points in the eruption, it's really been dominated by more blocky lava flows, where it's just rubble at the edge that's getting pushed along by the molten lava buried inside it, and that's very hard to sample. But the great thing about sampling the molten stuff is we know that exactly when that came out of the vent. But the other thing that we've been able to do is, because there are so many webcams set up watching this eruption, where we haven't been able to sample something or it's not been accessible, we've been able to pinpoint exactly where different bits of the lava flow came out and then solidified. So we can go along and collect that solid material, and we can tie it to an eruption date.
So have you already seen the composition changing?
Yes. So this is something we didn't expect to see, but in the first 4 weeks of the eruption, the composition changed quite quickly. And this is something we've not seen before for such a sort of primitive lava flow in Iceland. And when I say primitive, what I mean is it's coming almost straight from the mantle. It's not really spending much time in the crust and chemically changing in the crust. And generally, when we see eruptions like that have erupted hundreds or thousands of years in the past, then there might be a bit of variability, but it's generally pretty homogeneous basalt. Mm-hmm. Whereas this time we saw a change from lavas that were more depleted in elements like potassium and sodium perhaps, and trace elements, the elements that are there in very low concentrations. So it started off quite depleted in those, and gradually it evolved to being more enriched in those elements. Mm-hmm. And the ratios of the element concentrations also changed, and the radiogenic isotope ratios of the material changed at the same time. And so our understanding of that so far is we're seeing these different melts coming from different bits of the mantle, or different mantle components, different flavors of mantle, and the balance we're seeing coming out at the surface is changing over time. But since then, it's been pretty stable so far, but we're waiting for the next batch of analyses to appear, which should happen this week.
That's cool. So do you think this variation is because you've been able to do such robust sampling? Is I guess what we're sampling from much deeper time eruptions just a function of effectively just being able to sample whatever's on top, I guess?
It could be, yeah. And so when I say we've not seen this before, that's only partly true, because it's certainly true that we've not seen this before when we grind up a whole lump of lava and just analyze that. But we have seen similar things before in droplets of melt that have been trapped within crystals as they've grown in these lava flows, or within the magma that contributes to the lava flows. So we call these things melt inclusions. And the great thing about melt inclusions is they offer us an archive of the melts or the magmas that were present when the crystals were forming deep down in the crust, deep in the volcanic plumbing system, that then may get completely mixed out, or we might not see at the surface for other reasons. And so there's always a bit of skepticism when we look at those melt inclusion compositions, because we don't see those melts erupted at the surface. Are they really telling us something real? And so it's very nice to see in this eruption that these melts really do exist in this plumbing system. We see them in the melt inclusions, and we see the same variability coming out in the lava flow. And perhaps because of however these eruptions start, maybe you only ever see that variability at the very start of eruptions. And perhaps in the past, that variability has just been covered up by later lava. So we've got no hope of seeing it in these ancient lava flows.
I guess it's really cool to see what sort of a dynamic system chemically this is then. I guess it must, so how exciting is it to be there on the forefront, getting these analyses so rapidly after something is being collected? That must be really quite thrilling.
Yeah, I guess something I've always found really exciting about science is when you get a result, you're the first person who's ever seen that result. Yeah. And I think obviously I feel that for lavas that I've analyzed that were erupted thousands of years ago, but I think that you get that feeling even more so when you're analyzing material that didn't exist in a solid form until 24 hours beforehand. Yeah. And certainly at the very start of the eruption, when we had no idea what the composition of this thing would be, and whether it'd be really significant or whether it'd just be, you know, the same composition has erupted there over the last 1,000 years. And so it's very exciting to just get the data and then to see there was something different about it. And then I guess at every stage along the way, scientists here have made predictions about what it might do. We might not have publicized these predictions, but we've certainly made them amongst ourselves. And at the start of the eruption, everyone was saying, well, it'll probably only last for a few days, maybe a few hours. And then the predictions were, well, it's just going to be a boring composition. It's just not good. It'll just be the same as it's always been. It's going to erupt monotonous basalt that's not particularly special. It keeps surprising us. And then as soon as you settle into thinking you understand what it's doing, the eruption finds another way to mix things up. So once,
that's good.
For example,
keeps you on your toes.
Yeah, so I think once everyone got comfortable with the eruption happening and it being from this one vent, then whole sets of new vents opened up, which is quite exciting. And they opened up very close to where some of the infrastructure had been set up by the rescue team. So that was quite amusing to see all this infrastructure being packed away very quickly. And then it started fountaining a few weeks later. So, yeah, I'm just waiting to see what the next thing.
Yeah, I guess has this eruptive cycle been a bit different in the sense that I guess a lot fewer people have been able to travel out to Iceland? I'm guessing in normal times you'd have flocks of scientists from around the world descending on Iceland to look at this kind of thing. I guess has that impacted the way in which you've sort of gone about sampling or conducting any of your analyses or anything like that?
Yeah, I guess it has had, or must have had an impact in that way. There certainly have been teams of scientists coming out here. The whole, or at least since I've been in Iceland, the borders of Iceland have been pretty much open, certainly to Europe, and now they're open to, I think, most of the world. It's just you have to go through a week of quarantine.
Mm-hmm.
Right. And so there's been quite a few teams of scientists who I think maybe have been missing out on fieldwork, and if they've been able to come, they've just accepted the fact they need to go into quarantine to come and see this. But also now that people are vaccinated, you don't have to quarantine here if you've been vaccinated. So there's been teams coming in from the US, for example. Yeah. And I imagine that's only going to increase over time. But certainly in the first days of the eruption, even if you were going to fly out here, it'll still be a week or so before you could actually get to any rock to sample. So I guess we were aware that we really needed to collect material from that stage, the eruption, with the view that other people will be interested in doing work on it.
You said before, like basically it looks like this volcano is tapping potentially different parts of the mantle. So it might be good to zoom out a bit. I guess the question is like, what's causing Iceland? Like, what is there deep beneath Iceland that makes Iceland be there, and what are these volcanoes tapping?
Yeah, so Iceland is kind of a special place because it sits on the mid-Atlantic ridge, which is where new oceanic crust is being made through the entire length of the Atlantic Ocean. But most of this ridge is below water. You wouldn't know it's there unless you were sort of making all the careful geological measurements that people make to understand plate tectonics. But Iceland, you can walk around on this stuff. You can see new oceanic crust forming. And the reason that Iceland is above the level of, is above ocean level, is here the mid-Atlantic ridge coincides with anomalously hot mantle. So where you get anomalously hot mantle upwelling, then you get more magma being produced. And if you've got more magma being produced, you have more crust being formed. And so then you can start building the oceanic crust up until it's thick enough to rise above sea level. And you also have, because the mantle is hot, you have a buoyant effect where it's the buoyant material sort of pushing Iceland up a little bit as well. And so both of those things together mean that we're above sea level here. And the reason we think the mantle's anomalously hot here is we think it's part of the big convection system that operates in the mantle, where we're transporting heat, certainly from the lowest part of the mantle, from the core mantle boundary and the lower mantle up to the surface. And so we think Iceland's sitting on top of this mantle plume, which is really this part of this convection system. And that means that it's hot, but it's also, this plume is transporting material from deep down in the earth, which then melts and produces some interesting lava compositions.
Yeah, that's it's kind of mind-boggling to think about the scale of some of these things. And it often doesn't occur to me actually that Iceland is a mid-ocean ridge. And to think of it as just an ocean island, I sort of forget that it also intersects an ocean ridge, which is very cool.
Yeah, no, it's a huge amount of melt production going on here, because you're combining two different geological settings where you get magmas being produced into one place. So you get this double whammy.
Yeah, I guess your role then as a geochemist, I suppose, is then sort of untangling all the different sort of components within this plume. So I guess you mentioned it's transporting material from deep down, and my understanding is that sometimes you get remnants of old subducted slabs being fed into this to these plume systems, and then using chemistry you can sort of try and unpick all these different chemically discrete components. Is that right?
Yes, yeah, exactly. And there's been a huge amount of work that's been done over many decades trying to do this in Iceland. And so there's a huge amount of data. And I think that's partly because Iceland's a very easy place to come to and do field work.
Yeah.
There's a lot of material to collect, a lot of really good material to collect. So we can measure all the variability that you might expect. It's not all just one flavor of basalt that comes out all the time.
Yeah.
And so when people have been doing that, we certainly do pick up on different flavors of mantle. And so we get what we might call depleted mantle, which is more typical of the mantle that's melting under most of the mid-ocean ridge system. Then we get more enriched mantle, or which we generally link to these sort of recycled subducted slabs that you mentioned a second ago. And the reason we call that enriched is those are the components that tend to have higher concentrations of these trace elements, things like the rare earth elements that are there in, we measure them in amounts of parts per million. And so they don't really affect what the lava's doing, but they're a fantastic tool for geochemists to understand the processes behind what's going on. And then I guess the third main flavor of mantle we see in Iceland is stuff that's been linked to what we often call primordial mantle. And so that's the geochemical signatures that we link to that are mainly in the noble gases. So certainly helium isotopes, there's a big excess of 3 helium over 4 helium, and 4 helium is the helium that we see more often, and 3 helium hasn't really been produced on Earth since through its lifetime. And any 3 helium that we see, we expect to have been there at the Earth's formation. And so most of the mantle has very low amounts, but there seems to be this component in the Earth that has more 3 helium atoms, which most people think tends to mean it's probably very deep down in the mantle somewhere that's managed to stay hidden away. And we seem to be tapping some of that component in Iceland.
Yep.
somehow being brought up in the mantle plume that sits underneath Iceland.
And I guess it's I mean, I guess it's a quite a big plume, isn't it? So I guess part of your challenge, I suppose, correct me if I'm wrong, then, is to try and sort of unpick these different relationships between different components. I guess they're different depending on where you sample in Iceland, aren't they? So you can sample one area and you'll have a different configuration of components versus another. And I guess, is it fair to say there's a lot of debate in terms of exactly quite how many sort of different flavors there are, and there's a lot of subtleties, isn't there, I guess, that people like to argue about in terms of how all these things are intertwined and interacting with each other? Yes.
So whenever you can pick any combination of isotope ratio, and we're usually plotting isotope ratios when we try to unpick these mantle components, and you'll generally, if you plot up the data from Iceland, you'll generally find some nice lines of data. The data tends to line up, but depending on where you do it, you get different lines pointing in different directions. So if you take the northern volcanic zone, for example, you'll get the data lining up along one particular line. But then if you do the same on Reykjanes, or Reykjanes extends into the western volcanic zone, if you do it there, you get a subtly different line. So it might have a different gradient and be offset slightly. And so it's hard to understand exactly what's causing that. It could be that the mantle components are just very different in different parts of the plume. It could be that there's something to do with how the magmas are being generated and transported out of the mantle. That means they're mixing in some different way, where you seem to get these different end members appearing. But that's certainly an aspect of the work that I'm doing here, is trying to resolve some of that. But it's a difficult challenge, and yeah, it's something that we're making progress on, but it takes a long time and requires a lot of data and a lot of thinking.
Yeah, I guess one question that people might be thinking is, like, does where something comes from in terms of these different components have eventually any bearing on how it might erupt? And for instance, with this eruption, does any of the chemistry influence what people think it might do next?
Yeah, that's a really interesting question to ask. There's certainly been some suggestion that something different, or magmas coming from different mantle components, can influence how magmas erupt. And there's been some work done in Hawaii where they argue that there's more enriched melts that have more incompatible elements, or more trace elements, but they also have more volatile elements like carbon. And so they've suggested, well, if you have one of these more enriched magmas, it has more carbon, and so potentially it has more of an ability to erupt in maybe a more explosive way. I think it's, to my knowledge, no one's been able to make that link in Iceland. I think partly the problem with that might be, you think a lot of where magmas stall at depth within Iceland, we expect them to start losing their volatile phase pretty early on. So they might start losing some carbon very deep down in the crust. And so maybe that has an effect on, even if you bring in a really carbon-rich magma, maybe that carbon enrichment doesn't survive to the surface, so influence eruption style. But I guess another important aspect of that would be the other volatile elements like sulfur or the halogens, which can have really significant health effects. We might expect the more enriched magmas to have more of these elements, and so potentially you might have a higher risk associated with those. But also, especially with sulfur, depending on the magma composition, you can stabilize crystalline sulfide phases, which then remove some of the sulfur from the melt. And so it gets very, very complicated quickly. And this is part of the reason it's been very hard to untangle the relationship between mantle components and the eruptive behavior. But this is certainly something that we're monitoring with this eruption, is what we think the volatiles are doing.
There was an eruption a few hundred years ago, right, where there was a whole lot of fluorine came out, right? And thinking that lucky.
Yes.
The major health effect was fluorine. Is that a case where the fluorine was the result of the source, or I know nothing about Lackey. It's just a really interesting thought. Like, yeah, is that coming from the source of the melt, or is it to do with crustal processes happening along the way?
So I think the fluorine that would have come out in Lackey is ultimately derived from the mantle. I think making the comparison between an eruption like Lackey and an eruption like Petrographic, the ongoing eruption, the mass and the volume of magma is vastly different.
Right.
And so we can also make this comparison to Holothurine, which maybe sits somewhere between Petrographic and Lackey.
So Lackey was very big.
Yes, yeah. And so I think partly that's why it was so dangerous. It's just because there's along with a huge mass of lava, there was also a huge mass of volcanic gas coming out. And again, the same was true for Holothurine. There was a much larger mass of volcanic gas coming out. Fortunately, there's not really any settlements around Holothurine, but a big impact that they were monitoring there was, okay, the initial plume didn't have much of an effect, but because there's so much, it can then get transported around and still have a major impact. Whereas this eruption, because you've just got a much smaller mass of magma being erupted, the mass of the volatiles is also slightly lower, but it is closer to settlements. Mm-hmm. So certainly in Reykjavik, some days you can smell the volcanic plume. Oh, wow. It's not at the level where it's hazardous to most people. The Icelandic Met Office forecasts where the plume is going, and so people who may have breathing issues are aware that maybe today's the day to stay indoors and close the windows. But fortunately, and I think the same is true for Grindavik, even when the plume is blowing that way, it's generally staying below really hazardous levels, which is good. But another thing that people are monitoring is, are the gases or the hydrothermal circulation being affected by the eruption? Is there fluorine making it into the water sources nearby, for example?
Yeah.
And so far, as far as I know, we haven't seen any bad impacts there.
So Simon, so we talked a little bit then about how you use some of the geochemical analyses to answer questions about the mantle. So what sort of analyses and what sort of tools do you have available in your labs to actually address some of these questions?
Yes, so we're very lucky here that we've got a lot of pretty new analytical facilities and new labs, some of which only really came online in the last year or two.
Oh wow, really? That's cool.
Yeah, it's been fantastic timing for this eruption. It's been a good way of testing and selling a lot of these facilities, especially to people who've been funding all of this. But I guess I can talk through what we would do from the point where we get the samples back into the building. And so once we arrive back from the field, since a lot of the samples have been collected by quenching in a bucket of water, they're quite wet. So the first thing to do is you have to dry them in an oven. Even the samples that we collect that we didn't have to solidify ourselves, we may well have collected them in the rain. So they also need to be dried. It rains a lot here. But then for the analyses we do, the first step will be to start crushing the rocks up. So some of these might be a fairly coarse crush so that we can still extract crystals out. And those crystals we then might mount up into little epoxy discs and polish down so we get a nice flat surface that we can then analyze on an electron probe. And that's how we get the compositions of the crystals, and we can analyze any of the melt inclusions that have also been trapped as those crystals have grown. And then some of those crystals, we've sent them to the iron probe in Stockholm, the Nordsims facility. And the really nice thing with an iron probe is it's a very, very sensitive instrument. And so we can analyze concentrations of trace elements using a very, very small amount of material. And so we can measure the trace elements and so on. But then with the rest of the stuff that we've crushed up that's not crystals, we might crush it to a really fine powder. And then that fine powder we can dissolve and get it into solution. And then we'll measure the major elements, so the elements that really make up the rock. And we use a machine called ICP OES to do that. And people may have seen that we periodically publish, I think we're doing the magnesium content and potassium and titanium content of the lavas. And that's where that data comes from. And that data is available on the Institute of Earth Sciences website and Facebook page. So we've got a time series of how that's evolving.
Cool. I will pop a link to that in the episode description then if anyone wants to have a browse through that data. That sounds cool. Yeah,
we've really also written up some sort of more formal releases of some of the other data, which I can send you.
Yeah, absolutely. Yeah, feel free, and we'll drop any relevant links in the description. Yeah, if anyone wants to read more about that in the audience.
And then with some of the other material, we take that into our clean labs here. And so when I say clean lab, that's a lab that's been specially constructed to try and keep out any contamination from inside the lab. And the reason that we do that is in the clean lab, we dissolve up the material and start purifying it to analyze elements that are there in very low abundances. And so that's how we get the trace element analyses. So we measure all the rare earth elements and half the rest of the periodic table. But then we also purify for lead, neodymium, and strontium, so that we can then use the mass spectrometer we have here to get the isotope ratios. And that really allows us to fingerprint the contribution of these different mantle components. And so we've collected quite a bit of data doing that now. Certainly the isotope analyses are quite time consuming. And so we're still making our way through those. But we've got a paper that we're drafting at the moment that hopefully will be out reasonably soon with the complete data sets that we've been collecting.
Yeah, well, I was going to ask in terms of timings. I guess we're sort of talking on the order of weeks or months more, would you say? I guess, or
yeah. So at the start of the eruption, when we were all working full time on the eruption and we managed to put everything else to one side, then we could get a sample in and get an analysis out potentially the same day, if not the following day, certainly for the major elements and the electron probe work. Trace elements, that might take a few days to get through the chemistry for that. But then for the isotopes, I think we got the first data out within 2 weeks.
Oh wow, that's really cool.
Which was pushing it a little bit. Although I'm sure if we really wanted to be really speedy, we could condense it down even further, but not without quite a bit more work.
Yeah.
But usually it would take months to go through the whole process.
Yeah, I'm in the process of that kind of work at the moment. It's taken months.
Yeah, the downside of getting it done in 2 weeks is it took up most of the time of those 2 weeks.
Yeah.
Involved a lot of work in the evenings and weekends to get those samples through.
Yeah. Yeah, I guess my memory of doing that sort of chemistry is mostly just sort of popping in and topping up little beakers full of different chemicals and letting them evaporate and all that kind of stuff. I guess that's the time-consuming element, isn't it? It's just waiting for things to dry and waiting for things to digest.
And cleaning a lot of labware.
Yeah.
Yeah, it's really cool to turn this around into data in such a short time.
Yeah.
Yeah, I guess for comparison, there's a sample set that I've been working through exactly the same chemistry that I think took about 6 months. It's the same point that we managed to get this material to in 2 weeks.
Yep.
But then that's because everyone was working together and there was a big focus on getting this data out as quickly as we could.
That must be quite fun in and of itself. I don't know exactly your project or whatever, but often science can be quite solitary and you're working on your own things. So these occasional times where we work as big teams can be really fun, really enlivening.
Yeah. That's something I've enjoyed a lot with this. Everyone's working towards one goal.
Yep.
Everyone's sort of doing their own slightly different things, but all working together, which has been really nice. And we've been able to achieve quite a lot in a comparably short amount of time. There's quite a big team of us here at the moment, which has been really good.
Brilliant. Well, that sounds fantastic. So what are you hoping for in the future then for this eruption? Is your plans to continue to analyze at maybe a slightly sort of longer cadence or until it basically stops erupting? Or
yes, so we're still trying to get samples that's been erupted every week or two. I think we've pretty much got the sample every week so far, and we're going to keep analysing them and just keep monitoring to see whether there's any change in what's going on. I suspect it probably won't change very much now. We've not seen it change for a while, but we don't want to miss it if it does. But the other thing that we'll be doing is analysing the material in more detail. So so far we've done everything that we can do quite quickly, but there's a huge amount of other techniques that can be applied to this material. And so we're working, so some of that work's happening here, but we're also collaborating with people in the UK and the US and across Europe, using different facilities available.
Yeah, and I guess at the end of when it's all said and done, that's going to be such an amazing suite of samples, really, isn't it? I suppose that's amazing. I guess I mean, are there many eruptions that have been this well sampled from Iceland, or is it been slowly building up to a handful of sample suites over the past few years or whatever?
Yeah, I guess this eruption's been ideal in a lot of ways because it's so close to Reykjavik. You can go out there for half a day and come back with kilograms of material. And so that's meant that we can just collect a lot of material very regularly. That being said, I think for Fluorine, there was always a team out there collecting material, and I think the same is true of many other eruptions in recent history. I think the really new thing for this eruption is that it's been so closely monitored by the general public as well. We have so many different webcam streams available to us, so we can really see how the eruption's progressing and do really targeted sampling based on that. And then, because it's so close to Reykjavik, we can get the material back and analyze so quickly. And so then that also informs how we go and sample. And so when we were seeing these rapid changes, it meant that we could go out and sample every couple of days, for example.
Fantastic.
Very cool.
Well, Simon, that sounds excellent. Well, good luck for the rest of the eruption. Hopefully it continues to throw some interesting surprises at you. Before we wrap up, there's one last question very briefly that we like to ask all our guests that come onto the podcast. And really, so that's, if you hadn't fallen into the world of Icelandic geochemistry or geochemistry in general, and then you'd chosen perhaps to not go in an academic career, what do you think you might have gotten into?
That's a good question. I guess I guess within what I do now, there are two aspects that I really enjoy that I think that could be easily transferable to other careers. So one thing that I really enjoy doing is teaching. I really enjoy teaching undergraduate students, but also going into schools and talking with younger generation. And so maybe I could see myself doing more of a teaching role. But I also really enjoy, when I'm in the lab, enjoy playing with equipment and working out how things work and developing techniques. And so you know, I could imagine doing something in technology or something like that, where you're tinkering with things or creating machines, or something like that. I think.
Yeah, that sounds pretty cool. Yeah, it definitely is. Yeah, very fun playing around with Mass Specs, isn't it? Yeah, so that's something about the job I really enjoy.
On some days, at least.
Yes.
The days when you don't want to put them in the bin.
Yep.
Anyway, brilliant. Well, Simon, thank you very much for taking some time to chat to us. And anyone in the audience, again, we'll just have some links in the description if you want to read and more about this and have a look at some of the data that we've been talking about. As I said, good luck with the future. And well, to everyone watching, thanks very much. And we'll see you all again next week. If you want some more Earth and planetary science content, do check us out on all the social medias. The links will be in the episode description and on the screen right now. But until next time, see you all very soon. Bye, everyone.
Bye.
Bye.